And so I'd like to re-welcome you to the AMATYC webinar series. Our talk today is on the guided reinvention of sequence convergence with Dr. Michael Ortman and Dr. Craig Swinyard. This is sponsored by AMATYC, which is the American Mathematical Association of Two-Year Colleges. And this is to support one of our core values, which is enhancing personal growth. The views expressed by the presenters are not necessarily the views of AMATYC, but these presenters have been chosen by one of the committees of AMATYC. If commercial projects are mentioned, they are not necessarily endorsed by AMATYC. I'd also like to thank our school here and the Lift Institute, which is sponsoring all of these talks and providing the platform. And now I'm going to turn it over to Michael and Craig.
Okay, this is Mike. Thanks for having us here and inviting us. And this is a project that we've been working on for the past year, and we've been really excited about it. There is I guess it's on our last slide, a link to copies of the slides if you would like to. Kyung-Ha Rowe and Catherine Hart-Weber, all at Arizona State University. And with that, I'll go ahead and pass it off to Craig to get us started.
So one thing to begin with is thank you for coming. And Mike and I are really laid back. So if anyone what we thought we would do today to start out is just get a sense of formal limit definitions. Definitions, and that very well may have been in a calculus class, or perhaps some of you have taught advanced calculus or analysis, but maybe you guys can be thinking about those experiences as we give our talk today and study. We used advanced calculus, and when we thought about of sequence convergence, and so guided knowledge of the students, and they're more sophisticated, their informal understanding, convergence of informal understandings, but what challenges do they encounter as they go through that process? And secondly, how did the resolutions of those challenges support the students' reinvention? So that'll be the focus of our talk today. So some details about the teaching experiment. It was a 6-day teaching experiment. So this took place last summer with a couple of students from one of our collaborators, Jason Martin's second semester calculus class. And each session that we met with the students was about an hour and a half to 2 hours in length. And the goal was to have them reinvent 3 definitions. The first was sequence convergence, and the second was series convergence, and then the third was pointwise convergence. And the idea was that once the students had a nice strong formal definition of sequence convergence that meant something to them, that they might use that definition as they reinvented the definition of series convergence and so forth. And today we're going to just focus on the reinvention of the first definition. So this reinvention happened in what you could think of as an iterative process. And so on the very first day of the teaching experiment, we had the 2 students generate some examples and non-examples. And so we say, okay, if you think about what it means for a sequence to converge to, say, 5, what are all the qualitatively distinct examples you could draw for a sequence converging to 5? So they generated a bunch of different graphs, and the graphs that they generated, you can probably imagine. They had a sequence that was increasing towards 5, a sequence decreasing towards 5. They had a constant sequence right on top of 5. They had some alternating sequences, and a sequence which we'll refer to as the dying sine graph. So it was an oscillating function, or an oscillating sequence rather, that was decreasing in amplitude towards 5. So they generated those, and they decided, yeah, these are our examples that really capture the different ways that a sequence could converge. And then we also asked them to generate different examples for how a sequence could fail to converge to 5. And so they had a variety of non-examples that they generated. And once they had done that, we asked them they had their examples up on the board and their non-examples up on the board, and we said, okay, we want you to precisely characterize what it would mean for a sequence to converge to 5 then goes to infinity. And so they went through this iterative process, which we'll show you, where they wrote a definition, and then they would look at that definition in conjunction with the examples and non-examples that they had on the board, and they would evaluate that definition against those examples and non-examples, and often what they found was that their examples or non-examples would serve as counterexamples. They would realize, hey, there's something wrong with our definition here, and then they would get into a discussion of what the issue was, and they would try to resolve that issue, and then they would write a new definition, and then they would check their definition against their examples again, and this just kind of went in an iterative process over the course of about 3 days. And at the end of that 3-day process, they had a pretty good definition of sequence convergence. So there's the prompt you see there. A sequence converges to 5 as n approaches infinity, provided. And they went through quite a process of refinement over the course of 3 days. So their very first definition was pretty informal, and by fighting with all these issues, at the end of the 3rd day, or about halfway through the 3rd day actually, they had this nice final definition at the end. And it's worth noting that these 2 students that we worked with in our teaching experiment, neither of them had ever seen the formal definition of sequence convergence. So this wasn't something that they had remembered from a previous experience or that someone that had shown them. They really built this out of their own informal understandings. And that definition that you see there at the end is pretty solid when you compare it to the type of definition that you'd see in a textbook. So we're going to tell you a little bit about this iterative process that the students went through. Well, I mentioned that as the students were going through this process, they would come upon issues that they had to resolve. And Mike and I like to think about these issues really as opportunities. And these opportunities were opportunities for improving their definition. And we saw as we were analyzing the data that there were really 2 different types of opportunities. One is what we would describe as problems. And so these were issues that were raised by the students. That's an important piece there. Raised by the students most commonly as conflicts between what we would describe as their concept image and their stated definition. So just as a little bit of background for those who aren't as familiar with the literature, concept image is all the pictures and thoughts and words that a student would associate with a particular concept. And so these students both happen to have a pretty robust concept image of sequence convergence, and that was demonstrated both in the Calc 2 course but also based on the examples and non-examples that they generated and the conversations they had as they were in the process of constructing their definition. And so again, a problem then was something that the students raised, and they realized, hey, this is an issue that we have to resolve. And then there was a second opportunity type that Mike and I noticed in our analysis, which is what we would describe as a problematic issue. So these were issues that arose unbeknownst to the students, and most commonly as conflicts between our concept image as experts, so to speak, and the students' stated definition of concept image, or stated definition or concept image. So there were times where maybe they would refine their definition, and without realizing it, they had introduced a new issue. And it's worth noting also that a problematic issue could later become a problem for the students. Maybe there was something that was a problem back in the background that the students were unaware of that over time they became aware of. And often what we found is that when problematic issues became problems, then the students were more likely to focus in on those issues and resolve them. And we noticed that there were 2 different resolution types. One is what we would describe as an explicit resolution, and this is when the issue at hand was resolved via conversation that is focused on resolving that stated issue. So, for instance, the students construct a definition, they look at their examples and realize there's a particular thing they need to focus on and resolve, and the nature of their subsequent conversation is on resolving that specific issue. And if that issue gets resolved in that fashion, then we would call that an explicit resolution. But there were also times when an issue was resolved in the background, so to speak. So maybe the students were focusing on some other issue about their definition, and by fixing something else, one of their other either problems or problematic issues got resolved in that same process. So we would call these implicit resolutions. And as we looked at our data, we realized that we were, of course, an important element of this teaching experiment in terms of the roles we played as researchers. And we had 4 different roles that we saw ourselves playing. One was just guiding the process. So in the course of the teaching experiment, as the students were reinventing their definition of sequence convergence, as I'm sure you can imagine, there were moments where the ship was not steering towards productive waters. Maybe the students were starting to head down a path that was less productive in terms of resolving an issue at hand. Or, more importantly, the students maybe would have a lot of conversations out loud about, okay, we got to deal with this issue and we got to deal with that issue. And in the process of those conversations, they really would have pretty good ideas, but instead of capturing those ideas and getting those ideas down in a new definition, they would tend to continue to just converse and try to resolve yet another issue. So there were times when we would step in and say, hey, let's hang on for a second. Why don't we sit down and write a new definition that captures what you guys were just talking about? And that kind of kept them in that iterative process and allowed us to not lose important insights that the students had. Another role that we played was we were conflict producers. So there were times when we would ask questions that were designed to turn problematic issues into problems. So in other words, we would ask a question that might raise to the forefront an issue that the students didn't realize that they had. And hopefully by that question being asked, the students would recognize, hey, we got an issue here we need to resolve. And we found that when those issues became actual problems, the students were more likely to resolve them in meaningful ways. We also, at times, played the role of solution provider. So at appropriate times, and we'll say a little bit more about that later, we offered solutions to problems. And I believe Mike's going to give us a nice example of us playing the role of solution provider. So there were times when the students would have an actual problem they were trying to figure out, and they would struggle and really have pretty close ideas to what they needed. And we would perhaps step in and suggest a resolution to their problem when they really were ready to have that problem be resolved. And Mike will give us a nice example of that. And the last role that we played was that of elicit reasoning, and that's just because we asked for elaboration to produce rich data, so we acted in a way perhaps a little bit different than we would in the classroom. If we were in the classroom, we might not have as much opportunity to follow up with our students and ask them things like, okay, can you tell me more about what you were thinking there? What do you mean by this phrase? Because we were collecting data designed to produce rich data, we were reasoning elicitors as well. And I think I'm going to turn it back over to Mike here to tell you a little bit about
Thanks,
how
Craig.
these definitions came to be.
Am I coming through okay on audio? Great. Okay, so what we have here is the student's second definition that they created. And as you can see there, they're framing this in very typical kind of dynamic language, informal language that students use to talk about limits. And it mirrors the language that we tend to use when we talk about limits. You know, we talk about sequences, say, approaching 5 or approaching their limit value.